LHCb studies the nuances of the particle birth process. High-energy ion collisions in the Large Hadron Collider are capable of tearing quarks and gluons apart. How are secondary particles born from such a quark-gluon plasma? Further information on this subject is provided by the latest analysis of collisions of protons with protons or ions, observed as part of the LHCb experiment. When heavy atomic nuclei collide at the highest energies in the LHC accelerator, a quark-gluon plasma is created for an unimaginably short while. This is an exotic state of matter in which quarks and gluons, normally trapped in protons or neutrons, are no longer closely bound to each other. This state is not permanent. As the temperature decreases, quarks and gluons rapidly hadronize, i.e. reconnect with each other, producing streams of secondary particles diverging at various angles. The details of the hadronization process, a phenomenon of critical importance to our understanding of the foundations of physical reality, still remain a mystery. New clues have been provided by the recently completed analyses of collisions from the LHCb experiment, carried out with the participation of physicists from the Institute of Nuclear Physics of the Polish Academy of Sciences, IFJ PAN, in Kraków, which were published in the Journal of High Energy Physics. Hadronization occurs in times of the order of y octoseconds, i.e. trillionths of 1/trillionth of a second. At distances of the size of femtometers, i.e. millionths of 1/billionth of a meter, explains the co-author of the article, Professor Ph.D. Engineer Marcin Kucharczyk, IFJ PAN. We will not be able to observe phenomena occurring so extremely quickly and on such microscopic scales directly for a long time, and perhaps never. So we try to infer what is happening with the quark-gluon plasma by looking at some special quantum correlations between the particles produced in the collisions. We have been conducting such analyses for years. As the amount of processed data increases, we are gradually building an increasingly accurate picture of the phenomenon, he adds. What are quantum correlations? In quantum mechanics, wave functions are used to describe particles. If there are many particles in the system under study, their wave functions may overlap. Similarly to ordinary waves, interference occurs. When, as a result, the wave functions decay, they are called Fermi-Dirac correlations, and if they become stronger, they are called Bose-Einstein correlations. It was these latter correlations, characteristic of identical particles, that caught the attention of scientists. The researchers focused on the Bose-Einstein correlations that appear between pairs of pions, or pi mesons. Analyses of a similar type have already been carried out on data from other detectors operating at the LHC accelerator. But they concerned only particles diverging from the collision point at large angles. Meanwhile, the unique structure of the LHCb detector allowed physicists for the first time to look at particles emitted forward at angles deviated from the direction of the original beam by no more than a dozen or so degrees. The obtained results complement the picture of the phenomenon built thanks to measurements in other experiments at the LHC. The choice of the forward direction was not the only novelty. The analysis was performed for the so-called small systems, i.e. for proton-proton, proton-ion and ion-proton collisions. The last two cases are not identical. because in one case only one proton is moving at high speed, while in the other a nucleus consisting of many protons and neutrons. Scientists wanted, among others, to obtain information whether collective phenomena observed in nucleus-nucleus collisions, related to quark-gluon plasma, may also appear in collisions of smaller particle systems. Because all collisions were recorded using the same detectors and under the same conditions, we could easily check whether our correlations change in different configurations of colliding particle systems, says Professor Kucharczyk. Everything indicates that quark-gluon plasma can be created at the LHC even in collisions of single protons. The sources of secondary particle emission in proton-proton collisions seem to be smaller than in mixed collisions. An interesting relationship was also noticed between correlations and angles relative to the axis of the beam of particles produced in collisions. The observation of correlations in small systems has sparked a discussion about their origins. In particular, the intriguing question is whether they have the same source as in the collisions of heavy ions, and therefore, what conditions are actually needed to create a quark-gluon plasma. Some of the current models of this plasma assume the occurrence of collective phenomena related to flows. The results of our analyses seem to be closer to such hydrodynamic models, adds Professor Kucharczyk. But are we really dealing with quark-gluon plasma flows during hadronization? The announcement explains that currently existing theoretical models of the phenomenon need to be calibrated using data obtained from experiments. Despite this, none of the models can reproduce the measurement results with satisfactory accuracy. So it seems that before we learn the true nature of the processes taking place in quark-gluon plasma, physicists still have a lot of work to do, we read in the release. LHCb, Large Hadron Collider Beauty, is one of 7 experiments using particle detectors to collect data at the Large Hadron Collider, LHC, at CERN. The LHCb community consists of over 1,000 people from over 70 scientific institutes, representing 16 countries. Astronomers have spotted methane and water vapor on a distant exoplanet. Astronomers have spotted signatures of methane and water vapor in the atmosphere of the exoplanet WASP-80b. WASP-80b is a planet with a size and mass similar to Jupiter and is located about 163 light-years away, towards the constellation Aquila. The exoplanet WASP-80b was observed using the James Webb Space Telescope, JWST. Astronomers spotted the planet's transit. This is a situation when a planet passes in front of the disk of its star. Viewed from the perspective of a viewer on Earth, which causes its brightness to drop regularly. The degree of dimming and the almost imperceptible movements of the star caused by the planet's gravitational pull allow researchers to determine its size and mass. However, a planet with an atmosphere passing in front of its star not only dims the light, but also changes it, depending on the chemical composition of the atmosphere. Thanks to this, scientists can determine its composition. The results and description of the research were published in the journal Nature. By observing the exoplanet WASP-80b, scientists found signatures of water vapor and methane in its atmosphere. This planet orbits a red dwarf star 163 light-years away from the Solar System. towards the constellation Aquila. It is in a rather tight orbit and takes 3 days to orbit the star. WASP-80b has a size similar to Jupiter known from our planetary system. Temperatures on WASP-80b are around 550 degrees Celsius. For this reason, this world is called warm Jupiter. This is what astronomers call planets similar in size and mass to Jupiter in our solar system, which have a temperature intermediate between the temperature of hot Jupiters, which can reach nearly 1,200 degrees Celsius, and the temperature of cold Jupiters, such as ours, where temperatures reach around -150 degrees Celsius. Because the planet is so close to its star and both objects are so far from us, we cannot see this world directly, even with the most advanced telescopes such as Webb. Instead, scientists study the combined light of a star and a planet as it transits. We observed a situation where a planet passed in front of its star, causing the starlight we saw to dim slightly. It's a bit like someone walking in front of a lamp and partially blocking its light, said Taylor Bell from NASA and Arizona State University, the lead author of the paper. During this time, a thin ring of the planet's atmosphere was illuminated by the star, and at certain colors of light, where particles in the planet's atmosphere absorb light, the atmosphere appears denser and blocks more light, causing a deeper dimming, compared to other wavelengths where the atmosphere becomes transparent. This method helps scientists understand what a planet's atmosphere is made of by seeing which colors of light are blocked, Bell added. The resulting measurements, showing how much light is blocked or emitted by the planet's atmosphere at different wavelengths of light, were analyzed using 2 different models to simulate what the planet's atmosphere would look like. Both models showed the existence of methane and water vapor in the atmosphere of WASP-80b. Methane on Earth is produced as a result of geological processes, abiotic factors, or by living organisms, such as those that inhabit the vicinity of hydrothermal vents. They do not need oxygen to survive. They obtain energy by metabolizing carbon dioxide and hydrogen. In the process, they release methane. Therefore, finding this compound attracts the attention of scientists. However, finding traces of methane in the atmosphere does not mean that life exists there. Water vapor has so far been detected on several extrasolar planets. Methane has also already been detected outside the solar system. In turn, methane is quite common in our system. It has been detected many times, for example in plumes of material spewed from Enceladus geysers. For example, Titan, a moon of Saturn, has rivers and lakes filled with liquid methane. More on this in the text. Titan, an alien world extremely similar to Earth. Methane is not very stable, at least in the Earth's atmosphere. It photodissociates, i.e. breaks down into ions, and requires constant replenishment to maintain its presence in the atmosphere. If there is a lot of methane on a rocky planet, its source must also be large. On Earth, biological activity produces enormous amounts of methane. But this compound found outside Earth, as far as scientists can tell, is produced by abiotic factors. One such process is serpentinization. It is a natural process involving water, carbon dioxide and a mineral from the olivine group. Olivine is common on Earth and is the main component of our planet's upper mantle. We also found it on the Moon, Mars and some asteroids. Because WASP-80b is a gas giant, the existence of olivines is ruled out. But Uranus and Neptune in our solar system are also gas giants, and methane has also been detected in their atmospheres. Although methane attracts everyone's attention because of its connection to biology, this study shows us another side of methane. Its detection could help us understand how and where some planets formed and whether they migrated. For example, by measuring the amount of methane and water on a planet, we can infer the ratio of carbon atoms to oxygen atoms. This ratio is expected to change depending on where and when planets form in their system, the authors wrote in the publication. Astronomers can use this data to determine whether the planet formed close to its star or formed further away and then migrated into the system.